In the earliest decades of the 20th century, as Albert Einstein worked out the final pieces of his general theory of relativity, he could not have predicted just how far the mathematics would carry human imagination. Relativity described gravity not as a force pulling at a distance, but as the bending and curving of space-time itself. The equations were elegant, but they were also merciless in what they implied. Almost as soon as Einstein's work was published in 1915, a German physicist named Karl Schwarzschild found a solution that hinted at something almost unimaginable. The equations allowed for a region of space-time where gravity was so extreme that nothing, not even light, could escape. In later decades, this would be called a black hole. At the time, though, the idea was so strange that even Einstein doubted such objects could exist in the real universe. The concept seemed more like a curiosity hidden within mathematics than something that could shape the cosmos. For decades, most physicists set the notion aside, thinking it too unrealistic. Space, in their minds, might be sprinkled with stars, nebulae, and galaxies, but the thought that there could be invisible abysses swallowing all light and matter seemed like a step too far. As the 20th century moved forward, however, astronomical discoveries began to pile up. Telescopes, sensitive to X-rays, revealed powerful sources of energy scattered across the sky. Some of these could only be explained by matter spiraling into something compact and extremely heavy. Later, when scientists measured the motions of stars at the centers of galaxies, they found them whipping around at astonishing speeds, suggesting an unseen gravitational monster was anchoring them in place. These were not curiosities anymore. They were evidence. Over time, black holes were categorized by their size and mass. Stellar mass black holes, a few times heavier than the Sun, form from the collapse of massive stars at the end of their lives. Intermediate black holes, far more difficult to detect, are thought to exist between stellar-sized and giant ones, possibly born from collisions of smaller holes or from the direct collapse of dense star clusters. Supermassive black holes, weighing millions or even billions of times more than the Sun, dominate the centers of galaxies and power some of the brightest objects in the universe. There are even hypotheses about primordial black holes, tiny relics of the early cosmos, that could have formed just after the Big Bang. The story of black holes is not only told through theoretical work. Observational triumphs have cemented their place in modern science. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, together with its European counterpart Virgo, has detected ripples in spacetime caused by merging black holes. These signals confirm that such mergers occur throughout the cosmos, releasing more energy in a few seconds than all the stars in the observable universe emit in light over the same time. In 2019, the Event Horizon Telescope delivered the first direct image of a black hole's shadow, capturing the glowing ring of matter around the supermassive object in the galaxy M87. The image was proof that black holes are not just theoretical entities but real astrophysical objects that can be seen, studied, and measured. Even with this solid evidence, the fascination with black holes comes not only from their reality, but from the questions they raise. These objects sit at the boundary of what physics can currently describe. Einstein's equations predict them clearly, yet those same equations break down inside their depths. They are places where time and space fold in on themselves so intensely that human understanding falters. The early skepticism has now transformed into wide acceptance, but not without a cost. To accept black holes as real is to accept that the universe contains regions where known laws are stretched to their limits. This duality, reality confirmed, yet mysteries unsolved, makes black holes a perfect stage for the story of science itself. As we stand on the edge of this understanding, the next step is to examine the frontier of the black hole, the very surface that divides what can escape from what can never return. This is the event horizon, the defining boundary of a black hole, and it will guide us deeper into the heart of the mystery. The event horizon is often described as a point of no return, but in truth it is not a physical surface like the crust of a planet. It is a boundary in space-time, invisible and intangible, where the geometry itself ensures that no path outward exists. Imagine light rays streaming outward from a collapsing star. At first, even as the star shrinks, those rays can still escape, though they must climb a steeper and steeper slope in the curved space-time around them. But when the star's surface passes a critical radius, the slope becomes infinitely steep. Light no longer climbs away. Instead, the rays hover at the edge, trapped. That edge is the event horizon. The mathematics tells us something strange about how different observers experience this frontier. To an astronaut plunging past the horizon, there is no sudden jolt or flash. They cross the boundary without noticing anything extraordinary at that exact moment. To a distant observer, however, things look very different. As the astronaut falls, their image appears to slow, fading into redder and dimmer light until it vanishes. To the distant eye, they never seem to pass through. This dual perspective is not a trick of perception, but a consequence of relativity itself, where time and space are not absolute, but woven into geometry. Scientists have sought ways to confirm that such horizons exist in reality. Direct proof is impossible, since nothing from within can return. Yet the behavior of matter outside the horizon leaves signatures. Gas spiraling into a black hole forms an accretion disk, heating to millions of degrees and emitting X-rays that telescopes can detect. Sometimes, powerful jets of particles shoot outward at nearly the speed of light, launched by the twisted magnetic fields near the hole. These jets stretch across thousands of light years, testifying to the extreme processes at play. The existence of such phenomena, combined with the absence of any surface for matter to strike, is consistent with the presence of an event horizon. In recent years, the Event Horizon Telescope has added more weight to this picture. By linking radio observatories across Earth, it achieves the resolution to see structures as small as the silhouette of a black hole against its glowing surroundings. The ring of light observed around the black hole in the galaxy M87 is caused by photons skimming near the horizon, bent into almost complete circles by gravity. This so-called photon ring is a visible manifestation of space-time curvature at its most extreme. Beyond the technical achievements, there is a deeper lesson. The event horizon represents a boundary, not only for matter and light, but for knowledge itself. Physics can describe what happens outside, and relativity can predict what must occur mathematically inside. Yet no signal can escape to confirm those predictions. We are left with models, extrapolations, and indirect evidence, but never direct measurement. It is like standing at the shore of an ocean that swallows every probe we send into it. Nevertheless, horizons are more than abstract boundaries. They are the surfaces that shape galaxies, and possibly the universe itself. By swallowing stars and gas, black holes regulate the growth of galaxies. The energy released as matter falls in influences star formation across cosmic neighborhoods. In this way, the invisible edge of no return shapes visible structures on scales of millions of light years. Still, the event horizon is not the deepest mystery. It only marks the entryway to the true unknown, which lies within. At the center of the black hole, general relativity predicts the collapse of all matter to a singularity, a point of infinite density and zero volume. This singularity is not simply a location. It is the signal that the mathematics we rely on can no longer describe reality. Here, physics breaks down, and we must seek a new framework to move forward. Our journey, then, must pass from the horizon to the heart, where the singularity awaits. It is there that the puzzle of black holes challenges science most profoundly, demanding answers that stretch beyond Einstein's theory. Inside the mathematics of general relativity, the singularity is where density becomes infinite and space-time curvature has no bound. This is not a physical description, so much as a warning sign. When a theory predicts infinities, it usually means we have pushed it beyond its domain of reliability. For black holes, the singularity is the place where relativity alone can no longer be trusted. Einstein's equations describe how matter and energy curve space-time, but they do not incorporate the quantum rules that govern particles and fields at the smallest scales. Without those rules, the prediction of infinite density is incomplete. The famous singularity theorems developed by Roger Penrose and Stephen Hawking in the 1960s showed that singularities are not rare mathematical quirks, but inevitable consequences of gravitational collapse. As long as matter obeys certain reasonable energy conditions, collapse leads to a point where the theory must break down. These theorems deepen the conviction that general relativity, brilliant as it is, cannot be the final word. The laws of quantum mechanics must somehow be merged with gravity to resolve what happens inside. Scientists have proposed ideas to tame the singularity. Some approaches suggest that quantum pressure, similar to the forces that prevent white dwarfs and neutron stars from collapsing, could halt the contraction before reaching infinite density. Loop quantum gravity, for instance, envisions space-time itself as made of discrete loops, preventing volumes from shrinking below a certain scale. String theory offers another path, replacing point particles with vibrating strings that spread out interactions and avoid the infinities. Yet none of these proposals has been confirmed, and all remain theoretical attempts to reconcile two great frameworks of physics. Even without knowing the true resolution, black holes force us to confront the boundary between the known and the unknown. For astronomers observing from afar, the behavior of matter near the horizon agrees beautifully with relativity's predictions. Orbits of stars around Sagittarius A, in the Milky Way, match the equations precisely. Gravitational waves from merging black holes follow the templates laid out by Einstein's theory. But once matter passes the horizon, we lose contact. The singularity remains sealed away, inaccessible to any measurement. This limitation shapes both the power and the frustration of black hole science. On one hand, they are perfect laboratories, amplifying the effects of gravity so strongly that even small deviations from relativity might become detectable. On the other hand, their most extreme secrets remain hidden. We cannot send probes into their depths and expect them to return data. Our only path forward is indirect, reading the ripples in space-time and the glow of hot matter as clues to what lies within. The singularity is not only a physical enigma, but also a philosophical one. If the universe contains places where time and space truly end, then our understanding of reality has a boundary. Yet if the singularity is merely a signal that a deeper theory waits to be discovered, then black holes are doors opening toward the next revolution in physics. Either way, they challenge us to stretch imagination while staying rooted in evidence. As we close this first chapter, the picture that emerges is one of paradox. Black holes are simultaneously the most confirmed and the most mysterious objects in the cosmos. They are observed directly through gravitational waves, X-rays, and even images of their shadows. Yet their interiors elude every probe. They are triumphs of Einstein's theory, yet they also mark its failure. They are destructive in swallowing matter, yet creative in shaping galaxies. This tension sets the stage for what follows. The event horizon is not simply a border in space, but the gateway to questions about the ultimate nature of reality. In the next chapter, we will step closer to that frontier and examine in detail the horizon itself, the invisible surface that separates what can be known from what forever slips away. When scientists speak of the event horizon, they are describing not an object that can be touched, but a boundary drawn by the very structure of space-time. It is defined as the point beyond which no signal, not even a flash of light, can travel outward. To picture it, imagine a river flowing faster and faster as it nears a waterfall. A fish swimming upstream may succeed far from the brink, but once the current grows too swift, there comes a point where no amount of effort can carry it back. In this analogy, the fish is light, the water is space-time, and the edge of the waterfall is the event horizon. This boundary has a precise size, called the Schwarzschild radius, in honor of Carl Schwarzschild, who first derived the solution in 1916. For a black hole with the mass of the Sun, the radius would be about 3 kilometers. For Sagittarius A, at the center of our galaxy, with a mass of about 4 million suns, the radius is about 12 million kilometers. Despite the difference in scale, the principle remains the same. The larger the mass, the larger the horizon. Nothing can escape once it passes this invisible shell. For an object falling toward the horizon, the experience depends entirely on perspective. To the falling astronaut, time continues normally. They cross the horizon without drama, pulled ever inward. But for an observer watching from afar, time appears to slow for the astronaut as they approach the horizon. The signals from their clock arrive more and more delayed, their light stretched into redder wavelengths until they fade away. From that outside view, the astronaut never quite seems to cross. This effect, called gravitational time dilation, is not an illusion, but a real feature of relativity, showing how differently time can flow depending on the strength of gravity. Observational evidence for horizons comes from the way matter behaves in their presence. As gas swirls around a black hole, it forms a disk, heating to millions of degrees and releasing torrents of X-rays. If there were a solid surface instead of a horizon, matter would crash into it, producing a very different signature. The absence of such signals supports the conclusion that black holes possess true horizons. In addition, the Event Horizon Telescope has shown us the distinctive ring of light surrounding the dark shadow of a black hole. This ring is made of photons that skim along near the horizon, bent by gravity into nearly closed orbits. The fact that the image matches predictions so closely reinforces the idea that horizons are real physical boundaries, not just theoretical curiosities. The existence of horizons also influences the large-scale universe. When two black holes spiral together and merge, the vibrations they send into space-time depend strongly on the presence of horizons. The gravitational waves detected by LIGO and Virgo match the patterns expected from merging horizons, not from any kind of hard surface. These observations, consistent across dozens of detections, make it increasingly difficult to argue against the existence of event horizons. Yet the horizon is a one-way door. Nothing that enters can communicate back. This does not mean that horizons are empty of scientific interest. On the contrary, they are rich with implications. The horizon defines the boundary of information loss, leading to deep questions about whether the universe truly allows information to disappear. It is here that Stephen Hawking discovered in the 1970s that quantum effects near the horizon can produce radiation, slowly draining energy from the black hole over vast spans of time. That insight, born at the edge of the horizon, opened the most famous paradox in theoretical physics. What happens to the information carried by matter once it is swallowed? The event horizon, then, is more than a feature of Einstein's equations. It is a physical reality confirmed by observation, a gateway through which the known laws of physics give way to the unknown. Beyond it lies the singularity, the place where general relativity reaches its limits. As we move deeper into this exploration, the horizon stands as the boundary of certainty, marking the edge between what can be measured and what must be imagined. To imagine what truly happens as matter approaches the event horizon, scientists rely on both mathematics and analogy. Picture an astronaut falling toward a stellar mass black hole, several times heavier than the Sunday black port. At a great distance, the pull of gravity is strong but survivable. As the astronaut comes closer, tidal forces grow overwhelming. These forces arise because gravity is not uniform. The astronaut's feet, nearer to the black hole, are pulled more strongly than the head. The difference stretches the body, while at the same time squeezing it from the sides. Physicists call this spaghettification, a word that sounds almost whimsical, but describes a fatal and unavoidable fate. For small black holes, this stretching would happen well before reaching the horizon. For supermassive black holes, however, the horizon itself is so large that tidal forces at its edge are weak. In principle, an astronaut could drift past without immediate destruction, though nothing could prevent the inevitable pull toward the center later. The horizon's one-way nature has striking consequences for the laws of physics. In ordinary space, information can always be preserved in principle. Signals can be sent, trajectories traced, and interactions reversed. Inside the horizon, those rules seem broken. Whatever path an object takes, it points toward the singularity. This realization inspired Stephen Hawking to explore quantum effects near the boundary. His calculations showed that particle and antiparticle pairs could form just outside the horizon. Normally, such pairs annihilate, but near a horizon, one partner may fall in while the other escapes. To distant observers, it looks as though the black hole radiates particles, Over immense timescales, this Hawking radiation causes the black hole to lose mass and eventually vanish. The prediction of Hawking radiation raised a problem that has haunted physics ever since. If the black hole evaporates completely, what happens to the information carried by the matter it consumed? Quantum mechanics insists that information cannot be destroyed. General relativity suggests that anything beyond the horizon is lost forever. Reconciling these views has proven one of the greatest challenges of modern science. The information paradox is not merely a technical puzzle, but a sign that our deepest theories remain incomplete. Evidence for the horizon's influence is growing. The glow of X-ray binaries, the jets shooting from galactic centers, and the gravitational wave signals all paint a consistent picture of space-time warping to the brink of no return. Still, there remain alternative ideas. Some theorists propose that what we call horizons might be replaced by exotic surfaces just beyond, formed by new physics we do not yet understand. They look almost identical to black holes from far away, but would reveal differences under extreme scrutiny. Efforts to search for these differences are ongoing, using gravitational wave data to hunt for faint echoes that might betray such surfaces. So far, no evidence has confirmed these exotic scenarios, but the searches continue because they test the very nature of horizons themselves. The event horizon is therefore not only a defining property of black holes, but also a testing ground for the foundations of physics. Every observation that matches relativity's predictions strengthens our confidence in Einstein's theory. Every unexplained feature could point to something beyond. In this way, the horizon embodies both the success of modern science and the hope for deeper understanding. Yet the horizon alone is not the final mystery. It merely conceals what lies inside, where space-time curves toward the singularity. To confront that heart of darkness, we must follow the logic of relativity past the horizon, into a realm where known laws collapse and new ideas must take root. The singular presence of the event horizon in modern science has reshaped how we think about gravity and about the very limits of knowledge. When Carl Schwarzschild first solved Einstein's equations, the horizon was only a mathematical boundary. Today, thanks to decades of astronomical work, it has become a physical reality woven into the fabric of galaxies. The motions of stars near Sagittarius A trace graceful ellipses around an unseen anchor. The brightness variations of X-ray binaries reveal matter spiraling down to a hidden void. The direct images of the Event Horizon Telescope show the photon rings sculpted by light, orbiting just outside the abyss. Each of these strands of evidence converges on the same conclusion. Event horizons are not abstractions, but essential structures in the universe. And yet, even with this confidence, we remain unable to peer beyond them. The horizon is absolute in what it hides. No probe, no flash of light, no whisper of radio signal can ever slip back across the line. For science, which thrives on measurement and return of data, this is an unusual kind of barrier. We can describe, calculate, and predict what happens at the threshold, but we cannot confirm what lies beyond. The horizon, therefore, becomes not just a boundary in space, but a boundary of human inquiry. This has forced physicists to ask questions of principle. If information falls into a black hole and never returns, is it gone from the universe? If black holes radiate away and disappear, how is that information accounted for? The answers may determine whether the laws of quantum mechanics remain intact or require revision. The horizon is not only an astrophysical feature, but also a conceptual crossroads, where two great theories meet and clash. Astronomers, meanwhile, continue to push technology toward sharper views and subtler signals. Planned instruments like the next-generation Event Horizon Telescope and space-based gravitational wave detectors, such as the Laser Interferometer Space Antenna, promise to deepen our perspective. These tools may never look past the horizon, but they can measure with such precision that small deviations from expected patterns could hint at new physics. Even if the barrier cannot be crossed, its very edges may whisper secrets. There is a poetic irony in all of this. The event horizon, which seems to represent finality and silence, has instead become a source of profound discovery. By defining what cannot escape, it has illuminated entire galaxies. By showing where time slows and space bends without bound, it has sharpened our understanding of relativity. By refusing to release what it swallows, it has provoked debates that may one day unify physics itself. But the horizon is only the outermost layer of the mystery. Beyond it lies the singularity, the predicted collapse of space-time to a point of infinite density. The horizon tells us where knowledge ends. The singularity tells us why knowledge must go further. As we step into the next chapter, we will follow the logic of general relativity beyond the boundary to confront the strange and unsettling prediction that inside every black hole lies a place where the known laws of nature cease to function. The singularity sits at the heart of every black hole solution in general relativity. It is the endpoint of matter's journey inward, where the density grows without bound and the equations lose their meaning. For most of the 20th century, physicists wondered whether such extreme outcomes were simply artifacts of mathematical simplification, arising from assuming perfect symmetry. Perhaps, they reasoned, in a messy real universe, full of turbulence and irregularities, the collapse would stop short of any true singularity. Yet in the 1960s, Roger Penrose and Stephen Hawking demonstrated through rigorous theorems that singularities are not just curiosities of special cases. They are unavoidable whenever matter collapses under its own gravity past a certain limit. Their work showed that once an event horizon forms, nothing prevents the space-time within from contracting to a singularity. To grasp what this means, it is important to remember what general relativity describes. The theory links the distribution of mass and energy to the curvature of space-time. In ordinary conditions, such as the orbit of planets or the bending of starlight near the sun, the curvature is modest and well-behaved. But as matter compresses, the curvature grows stronger. The Penrose and Hawking theorems imply that under continued collapse, the curvature cannot stabilize. It must rise without end, creating a region where geodesics, the paths of particles and light, terminate abruptly. In more accessible language, this is a place where space-time itself comes to an end. Physicists hesitate to take this prediction literally. Infinite density is not something we expect nature to produce. Instead, most interpret the singularity as a warning sign that our current theory is incomplete. General relativity does not incorporate quantum mechanics, the framework that governs matter and energy at the smallest scales. When volumes shrink to microscopic levels, quantum effects cannot be ignored. The singularity is therefore understood not as a real physical point, but as a boundary where new physics must intervene. Still, the concept has profound consequences. If singularities truly exist in nature, they represent places where time and space are extinguished. No extension of geodesics means no future inside. If instead singularities are resolved by quantum gravity, then the interior of a black hole might be radically different from what relativity suggests. Ideas abound, from bouncing geometries that replace the singularity with a new expanding region, to discrete space-time structures that prevent infinite compression. None of these possibilities has yet been confirmed, but all are motivated by the recognition that relativity alone cannot suffice. For astronomers, this poses a challenge. The singularity is always hidden behind the event horizon, sealed off from direct view. No telescope can image it. No gravitational wave can escape its embrace. Our only tools are theoretical reasoning and indirect inference. This makes black holes unique laboratories. We know they exist. We can measure their influence. Yet their deepest regions remain shielded. They force us to stretch our theories into realms they were never designed to cover. The singularity also touches on deeper philosophical questions. If time itself ends inside a black hole, what does that mean for the notion of causality? If space-time cannot extend further, do we consider the interior a region of the universe at all? These questions are not rhetorical flourishes, but serious puzzles debated in physics departments. The singularity is both a triumph of mathematics and an admission of ignorance. It tells us that Einstein's equations are not the final description of reality. As the 20th century gave way to the 21st, new attempts to go beyond the singularity have multiplied. Loop quantum gravity suggests that space-time is quantized, made of finite loops that cannot shrink below a certain size. thereby averting the infinity. String theory, with its vibrating strings and extended brains, also offers mechanisms to smear out the collapse. Neither has yet delivered a definitive resolution, but both illustrate the drive to reconcile relativity and quantum physics. The singularity problem is not a minor detail. It is a central clue that points toward whatever the next great theory of nature will be. The journey into singularities is therefore not just a journey into black holes. It is a journey into the future of physics. By confronting the breakdown of current laws, scientists hope to glimpse the outlines of the laws to come. But before examining candidate theories, we must look at another mathematical consequence of relativity that once seemed promising as a way around the singularity: wormholes. The singularity theorems showed that under very general conditions, gravitational collapse leads inevitably to a place where space-time cannot be continued. Yet the theorems also left open a profound question. If singularities are unavoidable in the mathematics, are they also hidden from the outside universe? Roger Penrose proposed what became known as the cosmic censorship conjecture. It suggests that every singularity formed by gravitational collapse is cloaked by an event horizon. In other words, nature censors the singularity from external view, protecting the rest of the universe from its naked presence. This idea, though never proven, provides a comforting consistency. If true, then the singular breakdowns of relativity occur only where no observer can see them, preserving predictability in the universe at large. Still, physicists have explored whether exceptions might exist. Could there be processes that expose singularities to the wider cosmos? These so-called naked singularities would shatter our ability to make predictions. Without a horizon to hide them, the laws of physics outside could lose their coherence. Simulations of extreme conditions sometimes hint that naked singularities might be possible in special cases, such as rapidly spinning collapse or exotic distributions of matter. But no observational evidence has ever suggested their existence, and many researchers believe that some deeper principle prevents them. The absence of proof either way keeps the debate alive. The persistence of singularities across so many scenarios underscores the limitations of general relativity. Unlike quantum field theories, which can absorb infinities through renormalization, relativity simply runs into a wall. When density grows without bound, the mathematics stops. This is why many regard singularities not as features of reality, but as indicators that a more fundamental theory is required. Attempts to address this need take many forms. One is loop quantum gravity, which replaces continuous space-time with a discrete structure woven from finite loops. In this picture, collapse cannot shrink space-time volumes to zero. Instead, a minimum size exists, and the singularity is replaced by a bounce. Another path is string theory, which replaces point particles with tiny vibrating strings. These strings spread out the interactions, softening the infinities. In both approaches, the singularity is not a literal endpoint, but a signal that a new regime of physics begins. Despite these ideas, observational confirmation remains beyond reach. The singularity hides within the horizon, beyond the possibility of direct test. Yet astronomers still gather indirect clues. The precise shape of gravitational wave signals from black hole mergers matches relativity's predictions up to the horizon. But if future instruments detect small deviations, they could hint at new physics within. Similarly, the glow of accretion disks and the patterns of jets may one day carry subtle fingerprints of processes shaped by whatever resolves the singularity. For now, though, the singularity stands as a frontier. It is the line at which our best theory breaks, and it is the challenge that drives the search for quantum gravity. It is also a reminder that science is not only about confirming what we know, but about finding where our knowledge fails. In the story of black holes, the singularity is the moment where the narrative shifts from triumph to humility. As we move forward, the search for alternatives becomes irresistible. If collapse leads to breakdown, might there be other solutions within relativity that avoid this fate? Among the most intriguing of these are wormholes, tunnels that connect different regions of space-time. They first emerged from the same mathematics that gave us the singularity, offering a glimpse of something that might link rather than end the cosmos. In confronting singularities, physicists are reminded of earlier moments in science when infinities revealed deeper truths. In classical physics, the idea of an electron as a point particle led to infinite self-energy, a clear signal that the description was incomplete. Quantum electrodynamics resolved the issue by introducing renormalization, a new framework that removed the infinities and produced astonishingly accurate predictions. Many suspect that the singularities of black holes play a similar role. They are not telling us that reality itself becomes infinite, but rather that relativity, without quantum principles, cannot capture what truly happens. Stephen Hawking once described singularities as boundaries of predictability. Beyond them, the laws of science cannot determine the future. This was unsettling because science rests on the belief that given initial conditions and laws, the future can be calculated. A singularity breaks that chain. It is the physical embodiment of unpredictability. Yet if cosmic censorship holds, then this unpredictability remains trapped inside horizons, and the external universe continues to evolve in a lawful manner. The cosmos preserves its order by sealing its chaos away. For all their mathematical strangeness, singularities cannot be dismissed as irrelevant. They guide research into new physics and sharpen our understanding of what a complete theory must deliver. Any future theory of quantum gravity will be judged by whether it removes these infinities while still matching the successful predictions of relativity. If loop quantum gravity's discrete loops or string theory's extended structures can show how collapse avoids true singularities, they will offer not just mathematical elegance, but physical insight. Until then, singularities remain open wounds in our understanding. Their existence also raises profound questions about beginnings as well as endings. The Big Bang itself, when traced backward through relativity, appears as a singularity. This has led many to suspect that the same new physics needed to resolve black hole interiors will also explain the origin of the universe. In this way, the problem of singularities links the smallest scales with the largest, tying the fate of stars to the birth of cosmos. And yet, amid the weight of mathematics and theory, we must remember that black holes themselves are not abstractions. They are out there, pulling at stars, shaping galaxies, bending the paths of light. The singularities predicted within them might never be seen directly, but their presence influences everything we observe. Every time we watch a star swing around Sagittarius A or measure the ring of light around M87's giant black hole, we are indirectly feeling the tug of something our theories cannot yet fully explain. Thus, the singularity is not a dead end but a signpost. It points us toward the physics that lies beyond Einstein. It challenges us to find a theory that unites the smooth curves of relativity with the restless quanta of the microscopic world. In this challenge, black holes are not failures of science but its greatest opportunity. They demand that we push further, past the breakdown, towards something new. With this in mind, we turn to the next mathematical vision offered by general relativity, one that seemed to offer not an end, but a bridge. If space-time can curve so extremely that it closes in on itself, might it also curve to connect distant places? The idea of wormholes, first glimpsed in the work of Einstein and Rosen, arose as a possible escape from singularities, a pathway through the cosmos, hidden in the fabric of geometry itself. When Einstein and his collaborator Nathan Rosen studied the equations of general relativity in the 1930s, they noticed something curious. The mathematics that described a black hole could be interpreted in another way, as a connection between two regions of space-time. Instead of simply ending at a singularity, the solution could be extended to reveal a tunnel, a bridge that linked one sheet of space-time to another. This was the birth of the Einstein-Rosen bridge, later known as a wormhole. The idea captured imaginations because it suggested a radical possibility. Perhaps black holes did not only consume matter and light, but also served as gateways. If one could enter the throat of the bridge, maybe they could emerge somewhere else, perhaps in another part of the universe, perhaps even in another universe entirely. The mathematics allowed such a picture, and the very term wormhole reflected the analogy. Just as a worm burrows through an apple and connects two surfaces that appear far apart from the outside, a wormhole could join distant points of space-time through a hidden tunnel. Yet there was a problem. The original Einstein-Rosen solution turned out to be unstable. The bridge pinched off so quickly that nothing could travel through it. As soon as matter or light tried to enter, the geometry collapsed, sealing the passage. From the standpoint of general relativity alone, wormholes seemed more like ephemeral features of the equations than usable structures of the cosmos. They existed on paper, but not in practice. Later work explored whether wormholes could be stabilized. The mathematics showed that keeping a throat open required matter with very unusual properties, sometimes described as negative energy density. Ordinary matter, with positive energy, only tightened the throat, causing it to collapse. But exotic matter, at least in theory, could counteract this and hold the passage open. Quantum physics does allow small regions of negative energy to appear, such as in the Casimir effect, where quantum fluctuations between two metal plates produce a measurable force. But scaling such effects to astrophysical levels remains far beyond reach. No evidence has ever shown that enough negative energy exists in nature to prop open a wormhole. Nevertheless, the concept has remained scientifically useful. Wormholes serve as test cases in relativity and quantum field theory, forcing researchers to ask what is possible and what is forbidden. They sharpen our understanding of causality, energy conditions, and the limits of geometry. Even if no natural wormhole exists, the exploration of their mathematics has deepened insight into the structure of space-time. Popular culture has often taken the idea much further, portraying wormholes as cosmic subways, shortcuts across the galaxy, or portals into parallel worlds. While such depictions stretch far beyond evidence, they reflect the underlying fascination. The notion that space could fold upon itself so that distant points touch is irresistibly evocative. It transforms black holes from traps into possible gateways, even if only in imagination. But in serious science, wormholes remain speculative. The search for observational signatures has turned up nothing. No telescope has seen evidence of stars orbiting in ways that hint at hidden tunnels. No gravitational waves suggest their presence. As far as we know, the universe contains black holes that swallow and keep, not wormholes that connect and release. And yet, by considering wormholes, physicists uncovered other strange possibilities implied by relativity. If a black hole and its time-reversed mirror image were joined, the result would not be a bridge, but an object that forever expelled matter instead of consuming it. These theoretical constructs are called white holes, and they represent the next step in exploring the full breadth of Einstein's equations. The investigation of wormholes deepened in the latter half of the 20th century, as physicists asked whether relativity allowed any traversable tunnels at all. The consensus from early analyses was bleak. Without some form of exotic matter, the wormhole throat would collapse too quickly for even a photon to pass. The equations showed that ordinary matter contributes positive energy, which always adds to the gravitational pull. Far from stabilizing the tunnel, it ensures the bridge closes shut. Exotic matter, however, with negative energy density, could in principle provide a push against gravity and keep the throat open. This requirement may sound outlandish, but quantum physics provides a hint that negative energy can exist, at least fleetingly. The Casimir effect, first predicted in the 1940s and measured decades later, shows that two uncharged metal plates placed very close together experience an attractive force due to quantum fluctuations of the vacuum. The mathematics describing this effect reveals that between the plates, the energy density of the vacuum is lower than that of the surrounding space. In a sense, this is negative energy compared to the outside. Though the effect is tiny, it demonstrates that the vacuum is not empty but dynamic, and that energy conditions, once thought absolute, can be violated on small scales. Some theorists wondered whether similar effects could be harnessed on cosmic scales. Could quantum fluctuations, amplified somehow, provide enough negative energy to hold a wormhole open? Calculations suggest the amounts required are staggering, far beyond anything naturally available or technologically feasible. For this reason, wormholes remain in the realm of theory. They are not ruled out entirely, but the known laws of physics make them implausible in practice. Even if traversable wormholes could exist, they would raise difficult questions about causality. Relativity tightly links space and time, so a wormhole connecting two distant points might also allow time travel under certain conditions. By accelerating one mouth relative to the other, the time experienced at each end could diverge, potentially allowing signals or even travelers to arrive before they departed. This possibility alarms physicists because it threatens paradoxes, the ability to alter events that have already occurred. Many believe that some as yet unidentified mechanism, perhaps from quantum gravity, would prevent such violations, enforcing what Stephen Hawking once called chronology protection. Still, wormholes continue to serve as valuable theoretical laboratories. They provide a framework to test ideas about energy conditions, quantum fields in curved space, and the interplay between relativity and quantum mechanics. The study of wormholes has even influenced concepts like holography, where connections between distant regions of space can be described in terms of entangled quantum states. Despite the absence of evidence, wormholes remain one of the most intriguing possibilities offered by Einstein's theory. They show that relativity is not only a theory of gravitation, but also a generator of radical ideas about how space and time might be structured. Whether or not the universe contains such tunnels, the mathematics forces us to ask whether reality is more interconnected than appearances suggest. Yet if wormholes seem improbable, relativity also predicts another strange structure, the mirror image of a black hole. Instead of swallowing matter, this object would repel it, spewing out anything that approached. These time-reverse solutions are called white holes, and though no one has ever seen one, they represent the other side of the mathematical coin. Although wormholes have not been observed, their study has reshaped the way physicists think about space-time. In Einstein's era, gravity was reimagined, not as a force but as curvature. With wormholes, that curvature is pushed to its extremes, suggesting that the universe might allow shortcuts that defy ordinary intuition. Even if the actual cosmos does not contain such tunnels, the theoretical exercise of examining them clarifies what is possible under relativity and what is forbidden. It is in these thought experiments that science advances, not by indulging fantasy, but by testing the edges of the rules we know. One of the most profound impacts of wormhole research has been its connection to quantum theory. In recent decades, some physicists have proposed that wormholes may be linked to entanglement, the quantum phenomenon, where particles share states across distance. The conjecture known as ER equals EPR, named after Einstein-Rosen and Einstein-Podolsky-Rosen, suggests that entangled particles could be thought of as connected by tiny, non-traversable wormholes. This is not a literal bridge through which matter can pass, but a symbolic link, showing how gravity and quantum theory may describe the same phenomena in different languages. Such ideas are speculative, but they illustrate how wormholes, even as mathematical abstractions, inspire connections between the largest and smallest scales of nature. At the same time, wormholes remind us of the distinction between what is permitted mathematically and what is realized physically. Equations can be extended into strange and elegant shapes, but the universe may choose only some of those possibilities. Traversable wormholes, though consistent with certain mathematical conditions, require matter that has never been observed in the required amounts. The gulf between what is allowed and what is real is wide, and only observation can bridge it. So far, every search for astrophysical wormholes has come up empty. No gravitational lens has revealed the telltale distortions of a hidden tunnel. No unexplained orbital motion hints at unseen gateways. The cosmos, in this respect, seems to prefer simplicity over extravagance. And yet, wormholes remain valuable to keep in view because they demonstrate that general relativity contains more than black holes and event horizons. It is a theory rich with possibilities, many of which test our imagination and sharpen our understanding of the laws of nature. By studying these potential pathways, physicists learn where the boundaries of relativity lie and where quantum mechanics must step in. Wormholes are part of the dialogue between theories, even if they never become part of the observable sky. As our journey continues, we turn from bridges to their opposites, If a black hole swallows matter and light, and if a wormhole in theory could connect distant regions, then what would the time-reversed version of a black hole look like? The equations of relativity predict such an object. It is called a white hole, and it would be forever sealed against entry, while endlessly expelling matter and energy outward. Though none has ever been detected, the concept of white holes offers another window into the strange mathematical landscape revealed by Einstein's theory. When physicists explored the solutions to Einstein's field equations in the mid-20th century, they discovered that the same mathematics which predicts black holes also allows for their mirror image. These objects, called white holes, are like black holes in reverse. Whereas a black hole draws matter and light inward, never letting them escape once past the horizon, a white hole would permit nothing to enter. Instead, it would expel matter and radiation outward, as though ejecting everything that approached. To an outside observer, a white hole would appear as a perpetual source, forever pouring material into space without ever taking anything in. The existence of white holes follows from the time symmetry of Einstein's equations. If you take the mathematical description of a black hole and reverse the flow of time, you obtain a white hole. In this sense, they are not independent inventions, but necessary companions in the equations. However, mathematics does not guarantee physical reality. For a black hole, we have ample observational evidence. For a white hole, we have none. No astrophysical process is known to form them, and no signal in the sky has hinted at their presence. The properties of white holes are extreme. Nothing can cross their horizons from the outside. Any attempt to fall in would be repelled, not by a physical surface, but by the structure of space-time itself. Matter and light would instead be pushed away, radiating outward. In contrast to black holes, which hide their interiors from view, white holes would be nakedly visible, in the sense that whatever exists inside is constantly expelled. This makes them unstable in theory, since the matter they eject could accumulate outside and collapse back, undermining the conditions that sustain the solution. Despite these difficulties, physicists have studied white holes because they help clarify the completeness of relativity. If the theory permits black holes, it must also permit their time-reversed twins. Exploring why we see one but not the other sharpens our understanding of how the universe selects physical solutions from mathematical possibilities. In this way, white holes function as thought experiments, probing the edges of what space-time might allow. Speculative connections between white holes and other cosmic ideas have sometimes been drawn. Some researchers have suggested that the mysterious bursts of energy known as gamma-ray bursts could be related to white hole activity, though no evidence supports this view. Others have proposed that a white hole might mark the birth of a new universe, with matter and energy rushing outward in a fashion reminiscent of the Big Bang. These hypotheses are intriguing but remain untested, resting on analogies rather than observations. For mainstream astrophysics, white holes are regarded as unlikely. Their instability makes them improbable candidates for real cosmic objects, and the absence of any observational signature strengthens that conclusion. Still, their role in the mathematical structure of relativity ensures that they remain part of the scientific conversation. They are useful in exploring the full implications of Einstein's equations, even if they never appear in the sky. As we contemplate white holes, the narrative begins to shift from individual objects to broader possibilities. If black holes collapse inward and white holes spew outward, could there be a deeper connection between them? Some theoretical models suggest that the interior of a black hole might link to a white hole, not in our universe, but in another one entirely. This idea leads to the concept of baby universes, new regions of space-time that could bud off from black holes, carrying the seeds of cosmic creation within the darkness of collapse. White holes may never exist as physical entities, yet their study reveals important lessons about the symmetry of nature. General relativity is a time-symmetric theory, meaning that if a process is allowed in one direction of time, the equations allow a mirror image process when time is reversed. This symmetry explains why black holes and white holes appear together in the mathematics. But time in the real universe is not symmetric in the same way. Stars burn their fuel, expand, and die. Galaxies evolve. The cosmos itself expands, and cools. Entropy, the measure of disorder, always increases. The arrow of time points forward, and that arrow seems to forbid the sustained existence of white holes. Consider the collapse of a massive star. Gravity overwhelms the pressure of nuclear reactions, and the core implodes. If massive enough, the collapse continues past the neutron star stage and forms a black hole. This process is understood and observed, but there is no equivalent process that naturally creates a white hole. To form one, matter would have to emerge spontaneously from a horizon, perfectly coordinated in reverse. Such behavior runs against the grain of thermodynamics. In practice, it would require the universe to rewind itself in a way we never see. Physicists studying white holes also uncovered their instability. Imagine a white hole expelling matter into its surroundings. That matter lingers nearby, its gravity pulling back on the white hole. Tiny perturbations accumulate, and the system collapses. Instead of persisting, the white hole quickly turns into something else, often resembling an ordinary black hole. This instability suggests why the cosmos does not contain them, even though the equations permit them. Despite these obstacles, white holes have inspired speculative cosmological models. Some researchers suggested that the Big Bang itself could be interpreted as a kind of white hole, an explosion of space-time from which everything emerged. In this view, our universe may have originated as the interior of a black hole in a parent universe, with the singularity acting as a bridge to a new expansion. While imaginative, such scenarios remain outside the reach of observation. We cannot see beyond the cosmic horizon of our own universe, and no measurement so far supports the idea that it is connected to another. In theoretical physics, however, even unobserved ideas can be valuable. White holes highlight the distinction between mathematical solutions and physical reality. They force us to ask why some solutions are realized in the cosmos while others are not. This question goes beyond relativity, touching on the nature of time, entropy, and the laws that govern cosmic evolution. White holes, then, serve as reminders that mathematics can suggest possibilities broader than what nature chooses, and that science must separate the possible from the actual. As black holes and white holes are considered together, the door opens to another set of ideas. If a collapsing black hole could in some way transition to a white hole, might that process create an entirely new region of space-time? Could the singularity at the heart of a black hole serve as a seed for a separate universe? These questions lead to the speculative but scientifically motivated concept of baby universes, a topic that blends relativity with cosmology and pushes the imagination to its furthest edges. White holes also reveal how far theoretical physics can stretch when guided purely by mathematics. For decades, they remained as solutions on paper, haunting the edges of relativity, but never stepping into the sky. Some researchers explored whether they could exist on very small scales, perhaps as fleeting phenomena in the early universe when densities and energies were extreme. In those chaotic first moments after the Big Bang, quantum fluctuations may have allowed strange space-time geometries to appear briefly before vanishing. A tiny white hole in such a scenario would have been short-lived, evaporating almost as soon as it formed. No evidence remains of such events, but considering them helps scientists test ideas about the interplay between relativity and quantum theory in the most violent conditions imaginable. There is also a speculative link between white holes and black hole evaporation. Stephen Hawking's prediction that black holes radiate and eventually evaporate raises the question of what is left at the end. Some models propose that instead of disappearing entirely, a black hole could transform into a white hole at the final stage, releasing whatever information had fallen inside. This suggestion aims to address the information paradox, preserving the principle that information is never lost in quantum mechanics. The idea remains controversial, with no consensus on whether such a transition is possible, but it shows how white holes continue to influence modern debates about the foundations of physics. In popular imagination, white holes sometimes appear as cosmic fountains, endlessly producing matter and energy. In reality, if they existed, they would likely be brief, unstable, and subtle. Their scientific value lies not in being probable objects of the night sky, but in pushing theories to their limits. They sharpen questions about stability, causality, and the nature of time. They highlight that Einstein's equations contain more possibilities than the universe seems to realize, reminding us that physics is not only about what is observed, but also about what could be. By following the trail of white holes, we arrive at a profound possibility. If black holes are the ultimate sinks of matter, and white holes are their mirrored sources, perhaps together they describe a cycle of collapse and rebirth. Some models suggest that a black hole might form, collapse to a singularity, and then in some deeper theory bounce outward as a white hole, releasing its contents not into our universe, but into a new one. This is the seed of the baby universe idea, where each black hole becomes a gateway, not merely to destruction, but to creation. While still unproven, the concept builds naturally from the mathematics of relativity and the puzzles raised by quantum physics. With this, the discussion of white holes leads us to the threshold of cosmology itself. From singularities to wormholes and white holes, the path has carried us through the extremes of Einstein's theory. Now, in turning to baby universes, we enter the territory where black holes and the origin of the cosmos may be linked, and where the boundaries of physics blend with the beginnings of creation. The possibility that black holes might give rise to new universes is among the most daring ideas to emerge from modern physics. It begins with the recognition that singularities mark the breakdown of general relativity. If a collapsing star continues inward past its event horizon, the equations say it ends in a point of infinite density. But if that is merely a sign that relativity fails, then perhaps something else happens instead. Some theorists have suggested that at those extreme densities, space-time might not terminate, but instead rebound or branch, creating a new, expanding region of the cosmos. To observers outside, the black hole remains what it is, a dark object swallowing matter, but hidden behind its horizon, a separate universe might blossom, growing with its own space and time. This concept of baby universes has its roots in the mathematical extensions of Einstein's equations and in the search for a theory of quantum gravity. The idea is not that travelers could fall into a black hole here and emerge elsewhere in our universe, but that the collapse might pinch off and form a completely disconnected space-time. To us, the black hole would remain sealed. To the newborn cosmos on the other side, the black hole's singularity would appear as a kind of Big Bang, an initial burst from which expansion begins. In this sense, black holes could be cosmic wombs, giving birth to universes invisible to their parents. One of the most provocative versions of this idea came from the physicist Lee Smolin in the 1990s. He proposed what he called cosmological natural selection. In this hypothesis, every black hole generates a baby universe with slightly different physical constants. Universes that produce more black holes would therefore have more offspring, just as organisms that reproduce successfully pass on their traits. Over many generations, universes might evolve toward laws that favor black hole formation. Our own universe, abundant with black holes, could be one such survivor in this cosmic evolutionary game. Though intriguing, the proposal remains speculative, since no observation can yet test whether new universes actually form inside black holes. Other cosmological ideas intersect with the baby universe concept. The theory of cosmic inflation, for example, suggests that our universe itself began with a burst of exponential expansion, driven by a field of high energy. Some inflationary models allow for eternal inflation, in which inflation continues in pockets, each pocket budding into a new universe. If inflation can sprout new cosmoses, then perhaps black holes provide another route to the same outcome, their singularities replaced by regions of expansion. In both pictures, our universe may be one among countless others, each with its own laws and constants. Although there is no evidence yet for baby universes, the notion remains scientifically valuable because it addresses deep puzzles. It offers a potential link between the physics of black holes and the origin of our own cosmos. It raises the possibility that the constants of nature are not fixed by necessity, but shaped by a kind of cosmic selection. It forces us to confront the limits of what can be known from within a single universe. At the same time, scientists remain cautious. The idea of baby universes lies at the boundary between physics and philosophy, where speculation must be clearly separated from observation. No telescope can peer inside a black hole to confirm whether a new cosmos is forming. No gravitational wave detector can trace signals across universes. Until evidence arrives, these ideas remain hypotheses, inspiring but unproven. Still, they serve a purpose. They remind us that the universe may be far larger and stranger than what we see. They stretch our imagination while grounding it in the real mathematics of relativity and quantum theory. They keep alive the possibility that the cosmos is not a solitary island, but part of a grander multiverse, where black holes are not just destroyers, but also creators. As we follow this trail, the discussion naturally returns to the question of how relativity and quantum mechanics can be joined. The singularities that hint at baby universes are also the places where current theories collapse. To move beyond speculation, physicists must resolve the tension between Einstein's smooth spacetime and the grainy quantum world. This search for quantum gravity stands at the center of the next stage of our journey. The notion of baby universes naturally leads to questions about evidence, testability, and the boundaries of science. Lee Smolin's cosmological natural selection was one of the first attempts to frame the idea in terms of a hypothesis that could in principle be tested. If universes evolve by producing offspring through black holes, then ours should display constants of nature tuned not for life, but for black hole formation. For example, the masses of fundamental particles, the strength of forces, and the balance between nuclear and gravitational interactions might fall within ranges that maximize the number of collapsing stars. Smolin argued that if we could imagine a universe with different constants, we would often find fewer black holes, not more. This reasoning gave his hypothesis the spirit of natural selection, though on a cosmic scale. Critics pointed out that the proposal is difficult to evaluate. Our knowledge of how changing constants would alter stellar evolution remains incomplete. Even if it were true that our universe is optimized for black holes, this would not necessarily imply that universes reproduce through them. Correlation does not prove mechanism, and without a way to observe the process, the idea cannot be confirmed. Yet the attempt was valuable because it showed how bold speculation can be framed in terms of predictions, even if they remain beyond current reach. Other cosmological models approach the question differently. Inflationary theory, developed in the early 1980s, was designed to explain why the universe looks so uniform on large scales, and why it is flat and smooth, despite originating in a chaotic Big Bang. In its simplest form, inflation was a brief episode, but in many models, inflation never ends everywhere. Instead, it continues in isolated patches, each patch inflating into a new universe, while the larger space continues to grow. This eternal inflation picture produces a multiverse where new universes are constantly forming. In such a scenario, black hole baby universes may be only one of several mechanisms by which spacetime multiplies itself. The challenge for all these ideas is the lack of direct evidence. We cannot look beyond our cosmic horizon, and we cannot see into black holes. The evidence we do have, the cosmic microwave background, the distribution of galaxies, the signals from black holes merging, comes entirely from within our own universe. For now, the multiverse and baby universe hypotheses remain out of reach of direct observation. Some researchers argue that this makes them unscientific, while others contend that indirect predictions, such as patterns in cosmic structure or constraints on constants, could eventually provide tests. Despite the uncertainty, the study of baby universes has enriched theoretical physics. It has encouraged scientists to think about the origin of laws themselves. Are the constants of nature arbitrary, or are they selected by some deeper principle? If universes can reproduce, then perhaps what we call the laws of physics are not fundamental truths, but the outcomes of a cosmic evolutionary process. Even if this is not the case, asking the question stretches the horizon of inquiry. The concept also invites humility. Our universe may feel vast, but it could be only one branch in an immense tree of space-time. Each black hole might be a seed, each collapse an act of creation hidden from our view. We cannot yet know whether this picture is true, but by exploring it, we come closer to the frontier where relativity and quantum theory must meet. For if baby universes exist, they are born not from classical collapse alone, but from the quantum structure of space-time itself. It is here, in the unresolved clash between general relativity and quantum mechanics, that the next stage of our journey begins. To understand what really happens at the singularity, whether it ends in a dead point or gives birth to a new cosmos, we must turn to quantum gravity and the paradoxes it seeks to resolve. Speculations about baby universes highlight both the ambition and the limits of science. On the one hand, the mathematics of relativity encourages us to imagine that collapse might not simply end in oblivion, but could open into creation. On the other hand, the absence of observational access means these ideas remain beyond proof. For now, scientists walk a careful line, distinguishing between hypotheses grounded in established equations and stories that drift too far into fantasy. Baby universes sit in the space between, motivated by serious physics, yet unconfirmed by evidence. One way to think about them is as natural extensions of questions we already face. When a black hole forms, relativity predicts a singularity. But singularities are not physical objects, they are signals of a theory breaking down. To resolve them, some new description must take over. If that description allows space-time to bounce or branch, then baby universes follow naturally. In this sense, the idea is not a leap beyond science, but a consequence of confronting the limits of current theory. The real leap lies in asking whether such processes occur in the actual universe. Some researchers consider the possibility that baby universes might leave indirect fingerprints. If a black hole gives rise to a new cosmos, does that affect the way it evaporates through Hawking radiation? Could the information paradox be resolved if information is carried into the baby universe instead of lost? Such questions link cosmology with the deepest puzzles of quantum gravity. They remind us that the fate of matter inside a black hole is not only an astrophysical issue, but a problem tied to the foundations of physics. Philosophically, the idea of baby universes reshapes how we think about origins. It suggests that what we call the beginning of our universe might itself have been the end of another. It hints at a grand continuity in which universes beget universes, not through intention or design, but through the natural workings of gravity and quantum law. In this picture, creation is not a unique event, but an ongoing process scattered across the multiverse, with black holes as its engines. Yet, for all its allure, the hypothesis must remain tentative. Without observational access, we cannot yet distinguish between universes that truly multiply and those that remain solitary. Still, the act of considering such possibilities strengthens science by clarifying what is known, what is unknown, and what would be required to move forward. Baby universes illustrate that speculation, when carefully framed, is not a departure from science, but a step toward deeper understanding. As we leave this chapter, the path turns from speculation about new universes to the hard problem of reconciling the theories we already have. Black holes are arenas where relativity and quantum mechanics collide. Hawking's discovery that black holes radiate posed a question that still divides physics today. What happens to the information carried by the matter that falls in? To explore this paradox is to confront directly the need for a theory of quantum gravity, and to seek the bridge that unites Einstein's curved spacetime with the quantum rules of the microscopic world. In the 1970s, Stephen Hawking made a discovery that changed the way physicists thought about black holes forever. Until then, black holes were imagined as perfect prisons, swallowing everything and never releasing anything. Nothing, not even light, could escape from beyond the horizon. But when Hawking applied the principles of quantum field theory to the curved spacetime near a black hole, he found something astonishing. Black holes are not completely black, they radiate. The radiation arises from quantum fluctuations. In the quantum picture, even empty space is alive, with pairs of particles and antiparticles popping into existence for brief moments before annihilating each other. Near the horizon of a black hole, one member of such a pair can fall inward while the other escapes outward. To an observer far away, it appears as though the black hole itself has emitted a particle. Over time, This steady leak of radiation causes the black hole to lose energy, and therefore mass. In the far future, given enough time, the black hole would shrink and evaporate entirely. For a stellar mass black hole, this process would take longer than the current age of the universe, but in principle, it is inevitable. This insight was groundbreaking because it brought together the two great pillars of physics, relativity and quantum mechanics, in a single phenomenon. Yet it also unleashed a paradox that has dominated theoretical physics for decades. If a black hole evaporates away completely, what happens to the information about the matter that fell in? Quantum mechanics insists that information is never destroyed. The state of a system may change, but given the final state and the laws of evolution, one should always be able to reconstruct the past. General relativity, on the other hand, suggests that anything beyond the horizon is lost forever. Hawking's result seemed to put these two views in direct conflict. This problem became known as the black hole information paradox. It is not a minor technical issue, but a fundamental clash between the most successful theories of the 20th century. If information truly disappears, then quantum mechanics is incomplete. If information survives, then we must understand how it escapes from a region where relativity says escape is impossible. Resolving this paradox is seen as a key step toward discovering a theory of quantum gravity, the long-sought framework that unites the physics of the very large with that of the very small. Over the years, many possible resolutions have been proposed. Some suggested that information might leak out subtly in correlations hidden within the Hawking radiation. Others argued that black holes could leave behind stable remnants that store the information. Still others imagined that the interior of a black hole might be connected to the outside through new mechanisms, perhaps wormholes or holographic principles. Each idea carries strengths and weaknesses, and none has been confirmed. The paradox is not just abstract speculation. It has driven entire fields of research, from string theory to loop quantum gravity, each trying to show how information can be preserved without contradicting known physics. It has also sharpened the philosophical question of what it means for laws of nature to be consistent. Science depends on predictability. If information can vanish, then, in some sense, the universe itself forgets. The stakes are nothing less than the coherence of physical law. As we examine the approaches to this puzzle, we see how black holes have become laboratories, not just for astrophysics, but for the foundations of reality. They force theories to prove themselves under the most extreme conditions. They demand answers about the very fabric of space-time and the flow of information through it. In the chapters ahead, we will explore these proposed resolutions. Some of them come from the mathematics of string theory, others from the discrete structures of loop quantum gravity, still others from bold conjectures linking entanglement to geometry. Each offers a glimpse of how the paradox might be solved, and in doing so, how physics might take its next great leap. The first major line of attack on the information paradox came from string theory. String theory replaces point-like particles with tiny vibrating strings, whose different vibration modes correspond to the particles we observe. In the 1990s, researchers used string theory to count the microscopic states of certain black holes, known as extremal black holes, which have special charges that simplify their description. To their surprise and excitement, the number of possible string configurations matched exactly the entropy predicted by Hawking's formula. This was a powerful clue that black holes do not destroy information. Instead, the information might be encoded in the vast number of microscopic states that make up the black hole itself, even if those states are hidden behind the horizon. Another profound idea, also rooted in string theory, is the holographic principle. Inspired by work of Gerard Hooft and Leonard Susskind, the principle states that the information contained in a region of space can be represented on the boundary of that region. Much like a hologram stores three-dimensional information on a two-dimensional surface. Applied to black holes, this means that the information about everything that falls in may be encoded on the event horizon. From the outside, nothing crosses, but the horizon itself records the details. This perspective gained mathematical strength through the discovery of the ADS-CFT correspondence, which shows that a theory of gravity in a curved spacetime can be equivalent to a quantum field theory without gravity on the boundary of that space. If true in general, then black hole evaporation preserves information with no paradox. The information is never lost, but rather smeared across the horizon and re-emitted in the radiation. Loop quantum gravity, a different approach to quantum gravity, also offers a potential resolution. In this framework, space-time is not continuous, but made of discrete building blocks, woven together into a network. The discreteness prevents true singularities, replacing them with regions where space-time bounces rather than collapses infinitely. In some models, the interior of a black hole may tunnel into a new region, effectively avoiding the singularity and allowing information to continue its journey. These models suggest that black holes may eventually transition into white holes, releasing their contents. Though speculative, the idea illustrates how different quantum gravity approaches aim to rescue the principle of information conservation. Still, none of these solutions is without challenges. String theory, while powerful, remains untested experimentally and applies most cleanly to highly symmetric black holes, not the messy astrophysical ones scattered across galaxies. The holographic principle, though mathematically compelling, is best established in special spacetimes unlike our universe. Loop quantum gravity provides intriguing pictures, but the details of how information would emerge remain uncertain. The paradox persists not because there are no answers, but because none of the answers is yet complete. Meanwhile, new debates have arisen. In the 2010s, a proposal known as the firewall paradox suggested that if information is preserved, then the horizon itself cannot be a smooth, empty place as relativity predicts. Instead, it might be a searing wall of high energy that burns anything falling in. This radical idea sacrifices the gentle crossing predicted by Einstein's equations to save quantum mechanics. Yet such firewalls seem to contradict everything we know about relativity, leaving theorists divided. What unites all these efforts is the recognition that black holes sit at the frontier where quantum mechanics and relativity must meet. They are not just astrophysical curiosities, but essential testing grounds for the deepest principles of nature. Each attempt to resolve the paradox, whether through strings, holograms, loops, or firewalls, brings us closer to the long-sought theory of quantum gravity. And yet, for all the theoretical ingenuity, the cosmos itself may provide the final word. Observations of black holes, from gravitational waves to horizon-scale images, are becoming ever more precise. Subtle deviations from relativity's predictions could provide clues as to which resolution, if any, is correct. In this way, the paradox is not only a problem of mathematics, but a challenge to astronomy itself, inviting future instruments to probe the edges of knowledge. Despite decades of debate, the black hole information paradox has not yet been resolved. What makes it so enduring is that both sides of the argument rest on principles that seem inviolable. Quantum mechanics demands that information be preserved, while relativity insists that nothing escapes the horizon. Hawking radiation, predicted from the meeting point of the two theories, appears to force a choice. Either information is lost, undermining quantum mechanics, or relativity must be altered in ways we do not yet understand. The fact that both frameworks have been tested and confirmed to extraordinary precision makes the paradox even sharper. Over time, a subtle shift has occurred in the way physicists think about the problem. Many now lean toward the view that information is preserved, that somehow the laws of nature must protect it. The growing influence of the holographic principle, the successes of string theory in reproducing black hole entropy, and the continuing development of quantum information theory all point in this direction. Even Hawking himself, late in his life, conceded that information may escape after all, though he never provided a final mechanism. The debate, however, remains alive because the details of how this preservation occurs are still elusive. Black holes have thus become more than astrophysical objects. They have become laboratories for ideas about the ultimate structure of reality. Physicists now talk about spacetime as something that may emerge from quantum entanglement, about horizons as storage devices for information, about geometry itself as a byproduct of deeper principles. None of these ideas has yet been confirmed, but all of them are shaped by the need to resolve the paradox. This shows how powerful the influence of black holes has become. A puzzle raised by a theoretical calculation in the 1970s has driven entire fields of research for half a century. It has reshaped the way we think about quantum theory, relativity, and the very meaning of information. It has even drawn connections to areas far outside astrophysics, such as quantum computing and condensed matter physics, where the language of entanglement and holography now plays a central role. For observers, the paradox remains invisible. No telescope can watch information falling into a black hole and trace what happens to it. No detector can capture the faint trickle of Hawking radiation, at least not from astrophysical black holes. And yet, observations may still guide us. If we can test relativity near horizons with ever greater precision, we may see hints of new physics. If we can measure gravitational waves from merging black holes with exquisite detail, we may uncover patterns that betray the way horizons interact with quantum effects. These possibilities motivate the next generation of instruments, from the Laser Interferometer space antenna to the next generation Event Horizon telescope. In the end, the information paradox may not be resolved by theory alone. It may require the universe itself to show us the answer, encoded in signals that we have not yet learned to detect. The paradox, therefore, stands not only as a problem, but as a beacon, pointing toward the future of physics. It tells us where our current theories break down, and it guides us toward the observations that might reveal the new principles waiting beyond. With this, the story of black holes shifts once again from the realm of theory back to the realm of observation. We turn now to the experiments that can probe horizons, mergers, and jets, and to the instruments that may one day capture the whispers of new physics. For while the paradox frames the questions, it is observation that will ultimately lead us toward the answers. The paradoxes and speculations surrounding black holes would remain abstract curiosities if not for the astonishing progress of observational astronomy. For most of the 20th century, black holes were theoretical predictions, shadows cast by equations, but unseen in the sky. That began to change with the discovery of X-ray binaries, systems where a visible star orbits an unseen partner. The star's matter is drawn into a disk around the hidden object, heated to millions of degrees, and released as X-rays. The mass of the invisible companion can be measured through the orbital dance, and in many cases it far exceeds the maximum limit for a neutron star. These systems provided the first strong evidence that stellar mass black holes are real. The revolution continued with studies of galactic centers. Astronomers tracked the orbits of stars close to the center of the Milky Way, where they whirl around an unseen source, with speeds reaching thousands of kilometers per second. These orbits point to a central object with 4 million times the mass of the Sun, confined within a region smaller than our solar system. Nothing but a supermassive black hole can explain such a concentration. In 2020, the Nobel Prize in Physics was awarded for these measurements, which confirmed that Sagittarius A anchors our galaxy. Gravitational wave astronomy has opened an entirely new window. In 2015, the Laser Interferometer Gravitational Wave Observatory detected ripples in spacetime from the merger of two stellar mass black holes over 1 billion light-years away. The signal matched precisely the predictions of general relativity. Since then, dozens of similar events have been recorded by LIGO and its European partner Virgo, each one a cosmic collision releasing more energy in seconds than all the stars of the universe emit in light during the same interval. These detections prove not only that black holes exist, but that they merge, grow, and shape the cosmos in ways long predicted, but never before observed. Perhaps the most iconic observation came from the Event Horizon telescope. By linking radio dishes across the planet to form a virtual Earth-sized telescope, astronomers captured the first image of a black hole's shadow in the galaxy M87. The dark silhouette, surrounded by a glowing ring of hot plasma, matches the photon ring predicted by Einstein's equations. For the first time, humanity saw the outline of an event horizon. In 2022, the same technique delivered the first image of Sagittarius A, our own galaxy's supermassive black hole. Both images stand as triumphs of technology and theory combined. Each of these achievements has narrowed the space for speculation. Black holes are not just theoretical constructs, but observed astrophysical entities. Yet each has also raised new questions. The behavior of matter near horizons, the structure of jets that stretch for thousands of light years, the role of black holes in galaxy evolution, these remain open puzzles. Observations confirm the existence of horizons but cannot yet reveal what happens inside. They strengthen relativity's predictions, but also highlight the places where quantum effects might show themselves. The current generation of instruments has taken us to the brink of horizons. The next generation promises to go further. Planned upgrades to the Event Horizon Telescope aim to sharpen the images of photon rings, revealing finer details of the accretion flow and magnetic fields. Future gravitational wave detectors, such as the space-based laser interferometer, space antenna, will probe mergers of supermassive black holes across the universe, detecting signals too long and low in frequency for ground-based observatories. New X-ray telescopes, including the Athena mission, will measure the spectra of disks around black holes with unprecedented precision, tracing the flow of matter as it spirals inward. Together, these efforts may not only confirm relativity with greater accuracy, but also provide hints of new physics. As we stand at this threshold, it becomes clear that black holes are more than cosmic oddities. They are observatories in their own right, laboratories where gravity is so extreme that the universe itself conducts experiments beyond the reach of any human machine. By watching them, we test the foundations of theory. By listening to their waves and capturing their shadows, we glimpse the edges of reality. And by building new instruments to probe them, we prepare to confront the deepest questions raised by physics. In the coming decades, the frontiers of black hole observation will expand dramatically. The Laser Interferometer Space Antenna, known as LISA, is scheduled for launch in the next decade. Unlike ground-based detectors, which are limited by seismic noise and the size of Earth, LISA will fly in space with 3 spacecraft millions of kilometers apart, linked by lasers. This configuration will allow it to detect gravitational waves with much longer wavelengths, signals produced by mergers of supermassive black holes at the hearts of galaxies. These events, invisible to LIGO and Virgo, will become audible to LISA, opening a new chapter in gravitational astronomy. Each detection will not only confirm relativity in extreme conditions, but could also reveal subtle deviations hinting at new physics. Meanwhile, the Event Horizon Telescope is preparing for a next-generation upgrade called the NGEHT. By adding more radio dishes across the globe and increasing sensitivity, it aims to produce sharper images of black hole shadows. With greater detail, astronomers hope to map the dynamics of matter swirling near the horizon, tracing magnetic fields and plasma flows that power the enormous jets streaming from galactic centers. Such observations could test whether the photon rings perfectly match relativity's predictions, or whether small anomalies suggest quantum effects at play. X-ray astronomy will also see dramatic improvements. The Athena mission, led by the European Space Agency, is designed to probe the high-energy environments around black holes with unprecedented precision. By analyzing X-ray spectra, Athena will measure how matter spirals inward and how black holes spin. Spin is a crucial parameter tied to the history of how black holes grow and merge. It also influences the geometry of spacetime near the horizon. Precise measurements could confirm relativity's predictions or reveal discrepancies that point toward new theories. Other instruments will contribute as well. The Square Kilometre Array, a massive radio telescope project under construction, will study jets and accretion processes in detail, tracing how black holes influence galaxy evolution. High-energy gamma-ray observatories may uncover the processes by which black holes accelerate particles to near light speed. Each of these projects adds a piece to the puzzle, painting a richer picture of black holes not as isolated oddities but as engines shaping the cosmos. Some researchers are also searching for more subtle signatures. One possibility is gravitational wave echoes. If black holes are not perfectly smooth horizons but instead have exotic structures at the edge, collisions could produce faint, delayed signals, echoes following the main burst. Though no convincing detection has yet been made, the search continues. because even a single confirmed echo would revolutionize our understanding. Another possibility lies in precise timing of pulsars orbiting near supermassive black holes, where tiny deviations from relativity could reveal hidden effects of quantum gravity. All of these efforts illustrate how the paradoxes of theory inspire concrete experiments. The information paradox, the question of singularities, and the possibility of baby universes may sound abstract, but they shape the design of instruments and the goals of missions. Scientists know that the answers may not arrive quickly, but they also know that nature itself holds the solutions, encoded in the light, waves, and particles that black holes emit. By building the tools to catch those signals, humanity edges closer to uncovering truths that cannot be reached by theory alone. The story of black hole observation is therefore only beginning. The telescopes of today have given us shadows and waves. The instruments of tomorrow will give us details finer than ever imagined. With each improvement, we test Einstein's theory more rigorously, and we create the possibility of glimpsing the physics that lies beyond it. Despite the astonishing progress of recent decades, observations of black holes remain bound by a hard truth. The event horizon is a barrier no signal can cross. No telescope, no detector, no clever experiment can retrieve data from within. What we see are the effects of black holes on their surroundings, the way they bend light, twist magnetic fields, and stir matter into violent jets. These clues are powerful, yet they are indirect. The deepest mysteries, from singularities to baby universes, remain hidden. This limitation does not diminish the value of observation. Instead, it sharpens it. Every measurement of a star's orbit near Sagittarius A, every ripple recorded by LIGO and Virgo, every pixel of an event horizon telescope image constrains the space of possibilities. The closer observations match relativity, the less room there is for exotic alternatives. Conversely, any small deviation, if confirmed, could point the way to new physics. Observations cannot see past the horizon, but they can shape our understanding of what lies beyond by ruling out what is impossible. The challenge of probing horizons has led scientists to embrace creativity. If we cannot send probes in, we must let the universe do the experiment for us. Colliding black holes provide natural laboratories, producing signals that carry the imprint of their horizons. Accretion disks and jets act as amplifiers, revealing how black holes interact with their environment. Even the faint possibility of Hawking radiation, though far too weak to detect from astrophysical black holes, has inspired laboratory experiments that mimic horizons in fluids and optical systems. These analog models do not replace real black holes, but they demonstrate how physics at boundaries can be tested in surprising ways. Yet for all the ingenuity of technology, there will always be questions beyond reach. The formation of a baby universe, if it happens, is forever sealed from us. The exact nature of the singularity may remain hidden until a full theory of quantum gravity is achieved. Observations can constrain, suggest, and inspire, but they cannot dissolve every mystery. This is part of the human journey in science, the recognition that there are horizons not only in space-time, but in knowledge itself. And still, black holes continue to reward us. The universe has given us tools to test relativity in conditions unimaginable a century ago. It has given us signals that echo across billions of light years, carrying with them confirmations and challenges. It has given us images of shadows carved into the light of galaxies. Each new observation, each new mission, brings us closer to answers, even if the answers are partial. As we step from the domain of experiments into the realm of reflection, the story of black holes takes on a broader meaning. They are not only astrophysical objects, nor only puzzles for theorists. They are symbols of the scientific process itself, where curiosity drives us to the edge of what can be known, and humility reminds us of what lies beyond. In the next chapter, we will consider this human perspective more directly, tracing how black holes influence not only physics, but the philosophy of science and the way we think about our place in the cosmos. Black holes are not only objects of physics, they are also mirrors held up to human thought, forcing us to confront how science works, how knowledge grows, and where imagination meets evidence. Throughout history, the greatest revolutions in science have not come from adding small details, but from recognizing that the very framework of reality is different from what we believed. When Copernicus placed the sun at the center of the solar system, he did not only rearrange planets, he redefined humanity's place in the cosmos. When Einstein replaced Newton's force of gravity with curved spacetime, he did not only refine equations, he shifted how we think about time and space themselves. Black holes carry this tradition forward. They are real astrophysical entities, confirmed by observation, yet they also represent the collapse of our current understanding. For many people, black holes evoke a sense of awe tinged with fear. The very name suggests a devouring void. But in science, they symbolize more than destruction. They symbolize limits. They show us where relativity succeeds brilliantly and where it fails. They remind us that even the most elegant theories are incomplete. This is humbling, but it is also inspiring. Science grows not by pretending it has all the answers, but by recognizing the questions it cannot yet resolve. Black holes mark those questions in the clearest way possible. The philosophy of science teaches that theories are not final truths, but models. They describe reality within a certain domain, and outside that domain, they must be replaced. Newtonian mechanics still works perfectly for building bridges or guiding spacecraft, but in extreme conditions, it gives way to relativity and quantum theory. In the same way, relativity itself now approaches its boundary. Black holes point us to that edge, where quantum gravity must take over. To study them is to practice the very essence of science, to push theories until they break, and then to search for the next framework. Black holes also illustrate the delicate balance between speculation and evidence. Theories of wormholes, white holes, or baby universes are all rooted in serious mathematics. They extend from equations that have proven successful elsewhere, but without observational confirmation, they remain hypotheses. Science requires the discipline to keep these ideas in a separate category from established facts. At the same time, imagination is not a weakness, but a necessity. Without it, we would never design the instruments or ask the questions that bring us closer to the truth. Black holes show us that science thrives at the intersection of caution and daring. There is also a human lesson in the way black holes connect destruction with creation. They swallow matter and light, erasing stars and gas clouds, yet their presence regulates the growth of galaxies. Jets launched from their vicinity shape cosmic environments for millions of light years. In this sense, black holes are both destroyers and architects. They embody the paradox that the universe creates through collapse. That order emerges from what seems like chaos. For human thought, this is a reminder that limits and endings can also be beginnings, that what appears as darkness may conceal a deeper light. In contemplating black holes, we are therefore contemplating ourselves. We are asking how far our knowledge can reach, how much our imagination can stretch, and how science can proceed when confronted with mystery. Black holes are part of the cosmos, but they are also part of human culture, woven into stories, metaphors, and reflections. They remind us that the pursuit of science is not only about equations, but about meaning. As this chapter unfolds, we will look more closely at these philosophical dimensions. We will trace the parallels between black holes and earlier scientific revolutions. We will consider what it means for physics to encounter its limits, and we will reflect on how black holes, even if they are not gateways to new universes, are gateways to deeper understanding of what it means to know at all. In many ways, the role of black holes in science mirrors earlier revolutions in thought. When astronomers in the Renaissance argued that Earth was not the center of the cosmos, they were not merely moving our planet to another position. They were dismantling an entire worldview. Centuries later, when relativity showed that time and space were not absolute but elastic, that too required a shift in perspective, as profound as it was unsettling. Black holes now occupy this same role. They tell us that our current theories, powerful and predictive though they are, cannot be the end of the story. They press us to accept that we stand once again at the threshold of a deeper transformation in knowledge. For philosophers of science, black holes offer a case study in how theories are tested. Karl Popper once argued that for a theory to be scientific, it must be falsifiable. By that measure, black holes are excellent tests of relativity. The orbits of stars near Sagittarius A, the gravitational waves from merging binaries, and the photon rings captured by the Event Horizon Telescope are all sharp experiments that could have falsified relativity had they disagreed with its predictions. Instead, they confirmed it, sometimes with breathtaking precision. Yet, at the same time, black holes reveal where the theory must fail at singularities, at horizons that trap information, at places where the smooth fabric of space-time cannot be reconciled with quantum principles. They remind us that confirmation and failure are not opposites but partners. The same evidence that strengthens relativity also shows where it must yield to something new. The way scientists handle this duality is itself a philosophical lesson. Black holes require a discipline of humility. They demand that we distinguish carefully between what is observed and what is conjectured. They require us to resist the temptation to treat beautiful mathematics as physical reality without evidence. At the same time, they encourage boldness. Without daring to imagine wormholes, holography, or baby universes, we would never know which ideas might lead to testable predictions. Science progresses when humility and imagination are held together, each checking the other. There is also the matter of uncertainty. Humans crave certainty, yet black holes embody the unknown. They remind us that the universe is not built to satisfy our desire for clarity. For centuries, philosophers have wrestled with the problem of whether reality is ultimately knowable. Black holes sharpen that problem in a physical form. The horizon is not only a boundary in space-time, but also a metaphor for the limits of human knowledge. No matter how advanced our instruments, we may never peer beyond, yet the pursuit is not futile. By circling those horizons with light and waves, we still learn. The act of approaching the boundary expands understanding, even if the boundary itself remains uncrossed. This tension between the reachable and the unreachable has been present in science before. Quantum mechanics, for example, forced us to accept uncertainty as fundamental. Heisenberg's principle tells us that there are limits to what can be measured, not because of flaws in technology, but because of the nature of reality itself. Black holes extend this lesson to space-time. There are boundaries beyond which no information can return. In both cases, the challenge to human expectation has not been an obstacle, but a source of profound progress. By recognizing uncertainty as part of knowledge, not the enemy of it, science has thrived. Black holes remind us that what seems like a dead end may instead be an opening. They force us to develop new mathematics, new instruments, and new philosophies. They remind us that the unknown is not emptiness, but possibility. As the chapter nears its end, the question becomes personal. What do black holes mean for our view of ourselves in the cosmos? Are they symbols of insignificance, vast powers that dwarf human life? Or are they symbols of potential, showing that even in the most hostile corners of the universe, our minds can reach with understanding? In truth, they are both. They humble us by scale and mystery, and they exalt us by showing that curiosity itself can illuminate even the darkest places. Black holes have also escaped the confines of physics to become part of culture. They appear in novels, films, and art as symbols of annihilation, of mystery, of gateways to other realms. While many depictions drift into fantasy, they reflect something real: the power of black holes to capture imagination. Few other scientific discoveries have leapt so quickly from the pages of research journals into the shared vocabulary of society. When people speak of being pulled into a metaphorical black hole of work or emotion, they are drawing on the image of an inescapable force that science first revealed. This cultural presence shapes philosophy in subtle ways. Black holes are reminders that the universe contains places where human intuition fails. They are evidence that reality is not obliged to align with our expectations. In a world where certainty is often demanded, black holes stand as monuments to uncertainty. And yet, rather than paralyzing inquiry, they inspire it. They prove that mystery need not be the end of knowledge, but can be its beginning. The lesson extends to the philosophy of science itself. For centuries, debates have raged over whether science discovers truth or constructs models. Black holes show that both views may be necessary. They are real, observable entities, discovered by applying theories to data. Yet the models we build to describe their interiors are speculative, dependent on which theory we choose to extend. Science here is not about final answers, but about building bridges of understanding as far as possible, knowing that some of them will later be replaced. The story of black holes embodies the provisional nature of knowledge. For humanity, black holes also symbolize the paradox of insignificance and significance. They dwarf us in scale and power, swallowing stars as easily as dust. Yet our minds, small and fragile, have traced their shadows, measured their waves, and even photographed their outlines across millions of light years. In this sense, black holes remind us that knowledge itself is a form of strength. We cannot resist their pull, but we can understand it, and in doing so, we take part in the vast story of the cosmos. As we close this chapter, the journey has carried us from the physics of horizons and singularities to the human meaning of mystery. Black holes are both laboratories and metaphors, both scientific puzzles and philosophical mirrors. They stand at the edge of what we know and invite us to imagine what lies beyond. They are not gateways in the literal sense, not proven portals to new universes, but they are gateways in another sense. They open our minds to the next questions, the next theories, the next revolutions in science. In the final chapter, we return from philosophy to physics to reflect on black holes as cosmic laboratories. There we will gather what is known, acknowledge what is unknown, and see how the study of these dark giants may lead not only to answers about themselves, but also to the unification of the laws of nature. As the story of black holes draws to a close, it is clear that they occupy a unique role in science. They are not merely exotic objects lurking in distant galaxies. They are laboratories where the laws of physics are pushed to their ultimate limits. In their presence, gravity grows so strong that it bends light into circles, slows time to a crawl, and pulls matter into shapes beyond recognition. In their depths, the smooth equations of general relativity crash into the jittery rules of quantum mechanics. If we wish to find a unified description of nature, a theory that embraces both the vastness of the cosmos and the minuteness of particles, we must look to black holes. What we know about them is solid. Stellar mass black holes form from the collapse of massive stars, their existence confirmed by decades of observation of X-ray binaries. Supermassive black holes sit at the centers of galaxies, measured by the orbits of nearby stars and gas. Their mergers send out gravitational waves that ripple across billions of light years, detected with exquisite precision by instruments on Earth. Their horizons have been imaged directly by the Event Horizon Telescope, showing the dark silhouettes predicted by Einstein more than a century ago. In this sense, black holes are not mysteries, but facts. They are as real as the stars they swallow and the galaxies they shape. What remains unknown is equally profound. The singularity predicted at their centers is not a place we understand, but a signal of missing physics. The fate of information swallowed by horizons is unresolved, a paradox that continues to drive theoretical innovation. The possibility of baby universes, wormholes, or other exotic structures remains speculative, grounded in mathematics, but unconfirmed by observation. In these ways, black holes embody both knowledge and ignorance, both triumph and challenge. Because of this duality, black holes serve as natural experiments. They allow us to test relativity in the strongest fields imaginable, to measure time dilation and space-time curvature in conditions far beyond what can be created in a laboratory. They give us gravitational waves that act as fingerprints of cosmic collisions, waves that can confirm or challenge Einstein's predictions. They invite us to look for tiny deviations in signals that might point toward new theories. Every black hole is an experiment waiting to be read, every detection a data point in the quest to unify physics. In this way, black holes are more than astronomical curiosities. They are central to the scientific project. Just as the hydrogen atom once guided the birth of quantum mechanics, so black holes now guide the search for quantum gravity. By confronting us with paradoxes and puzzles, they force us to look beyond current frameworks. They remind us that even in a universe we think we know, there are still edges where certainty collapses and discovery begins. As this chapter unfolds, we will reflect on how black holes unify what is established, how they highlight what is speculative, and how they may lead us to the next great synthesis in science. We will see how, even if they are never proven to be gateways to other universes, they remain gateways to deeper understanding. Black holes test relativity in ways that no other objects can. The theory has been confirmed again and again in weak gravitational fields, from the bending of starlight by the sun to the slow drift of Mercury's orbit. But near a black hole, gravity is not weak, it is overwhelming. Here, the curvature of space-time becomes so extreme that even light cannot escape. Measuring how black holes behave is therefore a direct test of relativity at its most unforgiving edge. Every orbit of a star around Sagittarius A, every ripple of gravitational waves from a merger, is a chance to see if the theory still holds. So far, relativity has passed with remarkable accuracy, but each new observation pushes the test further, probing for cracks that might reveal the next theory. Quantum mechanics faces its own trial in the presence of black holes. The laws of quantum theory are built on probabilities, superpositions, and the principle that information cannot be destroyed. Yet when combined with the space-time geometry of black holes, those laws lead to the information paradox. Hawking radiation, though still undetected, is predicted by the marriage of quantum fields and curved space-time. It suggests that black holes eventually evaporate. If they do so completely, what becomes of the information they swallowed? No consensus yet exists, but every proposed resolution requires a new understanding of how quantum mechanics and relativity fit together. In this way, black holes force both theories to face their limits. The effort to resolve these conflicts has sparked some of the most creative ideas in physics. The holographic principle imagines that the universe itself may be a projection, with three-dimensional space emerging from two-dimensional information stored at its boundaries. String theory proposes that space-time and matter arise from vibrating strings and higher-dimensional objects, offering a way to count the microscopic states of black holes. Loop quantum gravity envisions space-time as a network of finite loops, preventing singularities and suggesting that black holes may one day rebound into white holes. Each of these frameworks is guided, in part, by the puzzles that black holes create. Observations continue to refine what is possible. The precision of gravitational wave measurements rules out some exotic alternatives to horizons. The images of black hole shadows confirm predictions of relativity to within a few percent. The absence of strange echoes in the data suggests that if new physics lurks at horizons, it is subtle. These constraints are not disappointments, they are signposts, narrowing the path toward the true theory. Every confirmation of relativity, every non-detection of anomalies, sharpens our understanding of where the new physics must hide. In this way, black holes serve as stepping stones toward unification. They show us where relativity and quantum mechanics clash, and they give us real phenomena to measure as we search for resolution. They are not just challenges but guides. By forcing us to reconcile the deepest theories of nature, they may lead us to a description of reality that embraces both the cosmic and the quantum. The laboratory of the black hole is not one we built, but one the universe built for us. As we reflect on their role, it becomes clear that black holes are not only destinations for matter, but also destinations for thought. They draw in ideas as powerfully as they draw in stars, concentrating our efforts where the laws of nature are most fragile. To study them is to study the very foundations of science itself. Black holes, in the end, embody the dual nature of science. They are boundaries and gateways at once. They set hard limits by hiding their interiors forever behind horizons, reminding us that not everything can be directly observed. Yet they also open paths to new theories, pointing the way to the physics that lies beyond relativity. They destroy stars and swallow light, but they also create meaning, shaping galaxies and shaping thought. They are cosmic laboratories not because we can control them, but because they test our ideas more ruthlessly than any experiment we could devise. To reflect on them is to see the arc of human inquiry. A century ago, they were dismissed as mathematical curiosities, too strange to exist. Now they are imaged, weighed, and heard across the sky. They anchor galaxies, collide in distant darkness, and leave ripples that pass through us. They have transformed from doubts in equations into pillars of evidence. And in the process, they have transformed us as thinkers, teaching us that the unknown is not to be feared, but to be pursued. Whether or not black holes are gateways to new universes, they have already served as gateways to new ways of knowing. They compel us to ask what it means for laws to fail, what it means for information to be preserved, what it means for time and space to be finite. They teach us that even at the edges of comprehension, science can proceed not with certainty, but with curiosity, humility, and persistence. Perhaps someday, the theory that unites quantum mechanics and relativity will emerge, and black holes will be understood in their entirety. Perhaps we will discover that singularities are illusions, that horizons are information screens, that collapse leads not to endings, but to beginnings. Or perhaps we will learn something even stranger, something no one has yet imagined. Whatever the outcome, the path to it will pass through black holes. They are the crucibles in which our theories are tested, the shadows against which our ideas take shape. For now, they remain as they are, silent, invisible, inescapable. And yet, through the instruments we build and the equations we write, they speak. They tell us about the strength of gravity, the flow of time, the structure of space-time itself. They remind us that even in darkness, there is knowledge to be gained. As we close this journey, we return to the question that began it. Could black holes be gateways to new universes? The answer is uncertain. Evidence points only to horizons and to singularities that defy our current theories. But in a deeper sense, the answer is yes. For whether or not they open to other cosmoses, black holes open our own universe to us. They expand our vision, deepen our understanding, and compel us to imagine beyond the limits of today. They are the universe's most powerful laboratories, and by studying them, we take part in the oldest human endeavor of all, to press against the boundaries of the unknown, and to step, however carefully, into the vastness that lies beyond. The story of black holes does not end with what we know today. It stretches into the future, into the experiments yet to be built, the theories yet to be refined, and the questions yet to be asked. If black holes are the crucibles of physics, then humanity is only at the beginning of learning how to use them. For generations, they were invisible and silent, their presence inferred only by absence. Now we can see their shadows and hear their collisions across the universe. The decades to come will push those senses further, transforming black holes from distant mysteries into precise laboratories of cosmic truth. The next generation of observatories will be our ships on this voyage. The Laser Interferometer Space Antenna will listen to the slow songs of supermassive black hole mergers, waves that roll through space-time with periods of minutes to hours. These signals will reveal not just collisions but entire histories of galactic growth, showing how the largest structures in the universe assemble over billions of years. Meanwhile, the next generation Event Horizon Telescope will sharpen our vision of horizons themselves, resolving details of magnetic fields and plasma flows so fine that they will allow us to test relativity at the percent level. Athena, with its extraordinary X-ray eyes, will dissect the innermost disks around black holes, telling us how they feed and how they spin. Each mission is a new sense, a way to feel the universe more fully. But perhaps the greatest future lies not in confirming what we know, but in uncovering what we do not. If black holes truly evaporate through Hawking radiation, their faint glow has yet to be seen. Detecting it may be impossible for stellar or supermassive holes, but miniature ones, if they exist, could reveal themselves through bursts of such radiation. Finding one would confirm quantum predictions in the most dramatic way. Similarly, the search for echoes in gravitational waves, the subtle aftershocks of horizons, may tell us whether they are smooth as relativity demands, or rough, with quantum structure. These are not guaranteed discoveries, but the pursuit itself sharpens science. Black holes also invite us to imagine how far human exploration might someday reach. We cannot travel to them with rockets, for their distances and dangers are beyond any spacecraft. Yet we can journey with thought and with instruments, extending our presence across light years and even across epochs. To future generations, black holes may be as familiar as atoms are to us, studied not as exotic monsters, but as natural features of a universe that yields its secrets to patience. The horizon, then, is not only a boundary in space-time, it is a symbol of the frontier of knowledge. Every age of science has its horizon. Once it was the structure of the solar system. Later it was the nature of atoms. Today, it is the depths of black holes. Tomorrow, it may be something even stranger. By pressing against horizons, we extend what it means to be human, reaching further into the unknown than those before us could have imagined. As this journey continues, black holes will remain at the center. They are not only remnants of collapsed stars or engines of galaxies. They are teachers, showing us where theories fail and where new ones must be born. They are guides, leading us to the unification of the great forces of nature. And they are companions, silent and ancient, watching from the dark as we learn to understand. The pursuit of black holes in the centuries to come may mirror the great scientific revolutions of the past. Just as Newton's laws unified the heavens and the earth under one framework of mechanics, and just as Einstein's relativity merged space and time into a single fabric, the study of black holes may unify the quantum and the cosmic. This is not only a technical goal, but a philosophical one. It asks whether the universe is governed by a single coherent set of principles, or whether our best theories will always remain fragments of a larger, hidden truth. The paradoxes black holes present ensure that this quest will not be easy. The information paradox alone has resisted solution for nearly 50 years, driving generations of physicists to develop string theory, holography, and loop quantum gravity. Each approach has illuminated part of the problem, but none has settled it. Yet, in this persistence lies the essence of science. Black holes remind us that the greatest challenges do not vanish with a single breakthrough. They demand patience, collaboration, and creativity across decades and across cultures. Future breakthroughs may come from unexpected places. Advances in quantum computing may provide insights into how information is stored and processed in systems with many degrees of freedom, shedding light on how horizons encode what falls within. New mathematical frameworks may reveal hidden symmetries in space-time that make the paradox less mysterious. Observational discoveries may surprise us, uncovering anomalies in gravitational waves or unexpected signals from galactic centers. The history of science teaches that answers rarely arrive where or when they are expected. Black holes will be no different. Beyond their scientific importance, black holes also carry meaning for humanity's future identity. As our species looks outward, building telescopes that reach across the universe and instruments that listen to space-time itself, we are extending our senses into realms that no life on Earth could once have imagined. Each detection of a merger or image of a horizon is a reminder that we are part of a universe vast enough to contain such wonders and clever enough to uncover them. In that sense, the study of black holes is not only about physics, it is about what it means to be human. Looking further still, one can imagine a time when knowledge of black holes reshapes technology. Although this remains far beyond our current abilities, some theorists have speculated about harnessing the immense energy of accretion disks, or even the Hawking radiation of microscopic black holes. Such ideas remain in the realm of thought experiments, yet they highlight how black holes push us to dream of futures beyond present limits. Whether or not such dreams are realized, they demonstrate the capacity of science to inspire imagination that stretches across centuries. Black holes therefore stand as bridges between past and future, between the physics we know and the physics we seek. They remind us that the universe is not static, but a journey, with each generation carrying the torch of curiosity further into the dark. Horizons are not ends, they are beginnings, and in that recognition lies the promise of discoveries still to come. In the final reflection, black holes emerge not simply as astrophysical phenomena, but as enduring symbols of the human search for knowledge. They embody the interplay of certainty and mystery. We know they exist. We have measured their masses, traced their orbits, and captured their shadows. Yet we also know that their deepest interiors remain hidden, beyond the reach of observation. This balance between what is established and what is unknowable is the essence of scientific exploration. Black holes remind us that truth is not a fixed point, but a horizon that shifts as we advance. They also symbolize resilience. For centuries, the idea of a black hole was doubted, dismissed as too strange to be real. It survived skepticism, was strengthened by mathematics, and was eventually confirmed by observation. Today, it stands as one of the most robust predictions of relativity, a triumph of theory validated by experiment. The journey of the black hole from speculation to evidence reflects the journey of science itself, a process of doubt, persistence, and eventual clarity. In philosophy, black holes serve as metaphors for limits, for boundaries we cannot cross, but they also show that such boundaries are not barriers to meaning. Instead, they are invitations. Horizons challenge us to ask what lies beyond, to imagine new theories, and to build new tools. In this way, black holes do not close off inquiry. They expand it, driving generations of thinkers toward deeper understanding. For humanity, they are reminders of scale. They dwarf our planet and our lives, yet they yield to our intellect. We cannot escape their pull, but we can grasp their nature with mathematics, telescopes, and imagination. In that sense, they affirm both our smallness and our greatness. They humble us with the vastness of the universe and honor us with the capacity to comprehend it. As we conclude this journey, the question that opened it remains unanswered. Could black holes be gateways to new universes? Perhaps. The mathematics allows it, but the evidence is silent. What is certain is that black holes are gateways in another, more profound sense. They open pathways to the future of science. They lead us toward the unification of quantum mechanics and relativity. They inspire new generations of scientists, philosophers, and dreamers. They remind us that the universe is richer and stranger than we can yet conceive, and that every horizon reached reveals another beyond. So we leave black holes where they are, scattered across the galaxies, silent giants shaping the stars. They remain mysteries, but mysteries of a fruitful kind, mysteries that give direction to inquiry. Whether or not they open onto new universes, they have already opened our universe to us. And in the darkness of their horizons, we find not despair but wonder, not endings, but beginnings. Every story in science eventually arrives at an edge, a place where what is known runs out, and only questions remain. Black holes bring us to such an edge, more directly than any other objects in the universe. They stand as both confirmations and contradictions, proving Einstein's theory with stunning precision, while also revealing where it must fail. They offer us shadows and waves that confirm relativity's brilliance, and at the same time, they present singularities and paradoxes that defy understanding. They are the crossroads of physics, the meeting point of certainty and mystery. To reflect on black holes is to reflect on the nature of knowledge itself. We began by asking whether they might be gateways to new universes. The evidence cannot answer. Perhaps they are, perhaps not. What we can say with certainty is that black holes are gateways to discovery. They have driven the development of gravitational wave astronomy, transformed our ability to image the cosmos, and inspired new mathematical frameworks that may one day unify quantum theory and relativity. Even in silence they speak. Even in darkness, they illuminate. The journey through black holes also teaches us humility. We have seen how each generation of science pushes closer to the horizon, only to find that the horizon recedes. This is not failure, but progress. Science is not about reaching a final truth, but about extending the circle of understanding. The unknown is infinite, yet every advance reshapes how we see the universe and ourselves within it. Black holes embody this lesson. They are mysteries without end, Yet each attempt to study them deepens our grasp of nature. They also teach us wonder. To imagine a star collapsing into a point, to picture light bent into circles, to listen to space-time itself, ringing from a collision across billions of years. These are experiences that enlarge the human spirit. Black holes may be indifferent to our curiosity, but our curiosity transforms them into meaning. They are not only astrophysical realities, but also symbols of our quest to understand, our refusal to stop at what is comfortable, our drive to press against the unknown. As we close, we leave black holes where they belong, scattered through the galaxies, silent engines shaping the cosmos. They will continue to merge, to feed, to launch jets, to sculpt the growth of stars and galaxies long after our species is gone. And yet, as long as there are minds to wonder, they will remain more than objects. They will remain questions, invitations, and guides. The ending is not an answer, but a horizon. And like every horizon, it is not the final limit, but the beginning of the next journey. In the long arc of human history, black holes will stand as one of the milestones of discovery. They will be remembered alongside the recognition that Earth orbits the Sun, that atoms form the fabric of matter, and that the universe began in a hot, dense state. Each of these revelations redefined our place in the cosmos, pulling us away from illusions of centrality and toward a deeper humility. Black holes carry this same power. They remind us that the universe contains realms where our best theories unravel, where time and space lose their familiar shape, and where imagination must stretch beyond precedent. And yet, even as they humble us, they also affirm the reach of human reason. It is extraordinary that creatures evolved on a small planet around an ordinary star can predict, through mathematics alone, the existence of objects so strange that not even light can escape them. It is even more extraordinary that we can then build instruments to confirm those predictions, capturing the faint echoes of their collisions and the delicate silhouettes of their horizons. This is science at its most audacious: to see the invisible, to hear the silent, to understand the incomprehensible. Looking forward, black holes will remain companions on humanity's intellectual journey. They will guide the development of new physics, challenge each new generation of thinkers, and stand as reminders of the unfinished nature of knowledge. Perhaps one day, the theory that unites quantum mechanics with relativity will dissolve their paradoxes. Perhaps one day, we will know whether singularities truly exist, or whether collapse gives way to rebirth. Or perhaps the universe will always keep part of their mystery sealed, ensuring that curiosity never finds an end. But the deeper meaning is not in whether we solve every problem. It is in the act of striving. Black holes symbolize the courage of inquiry itself, the willingness to confront the unknown, even when answers seem impossibly far. They are cosmic teachers, showing us that science is less about possession of truth than about pursuit of it, less about certainty than about wonder. As the horizon closes around this narrative, one thought remains. Black holes are not merely endpoints in the lives of stars or in the paths of galaxies. They are also reminders that in endings lie beginnings, that collapse can give rise to creation, that silence can carry meaning. The same truth applies to science and to humanity itself. Each horizon we reach reveals another, and each limit we encounter opens to a deeper question. In this sense, black holes are not the end of the story, but the beginning of many more yet to be told. In the final vision, black holes stand as monuments to both the vastness of the cosmos and the resilience of the human spirit. They are the universe's way of showing us the scale of mystery, but also our capacity to reach toward it. When we imagine their interiors, when we trace their shadows, when we listen to the space-time tremors of their collisions, we are not merely studying distant objects. We are participating in a dialogue with the universe itself, a dialogue in which silence is as meaningful as sound. Black holes remind us that knowledge is always provisional. We once thought the Earth was the center of creation, and we learned otherwise. We once thought space and time were unchanging backdrops, and Einstein showed us they bend and flow. We now think of black holes as collapsed stars and cosmic engines, and perhaps one day, we will discover they are something far stranger. Each stage of understanding is not an end, but a horizon. The horizon does not deny us the future. It defines the direction we must travel to reach it. The ultimate legacy of black holes may not be in the answers they provide, but in the questions they compel us to ask. Could space-time itself be emergent from quantum information? Could collapse be creation in disguise? Could our universe be one among many, born in the darkness of another? These questions may not be resolved in our lifetime, but they are now part of humanity's inheritance, carried forward as surely as starlight crosses the void. As we close, imagine the night sky. Among the stars, invisible to the eye, countless black holes drift. Some are the remnants of ancient suns. Some are titans at the hearts of galaxies. Some are merging in silence, sending ripples that will wash across Earth centuries from now. They are out there, shaping the universe, shaping us. We cannot see them directly, but we know they exist. And knowing that is enough to remind us that mystery is not the absence of understanding, but the promise of more to come. So the story ends as it began, with a question. Could black holes be gateways to new universes? The universe does not answer in words. It answers in silence, in gravity, in light bent into rings, in waves stretched across time. It answers by existing. And in that existence lies an invitation to wonder, to explore, to continue. The end is not the end, it is the horizon.